Right, let's take a look at how we can synthesize these ethers. So if we want to synthesize something that's very simple and symmetrical, so both sides of the ether are the same, we can do this from primary alcohols. So for example, we have ethanol over here. What we can do is we can just add some acid as a catalyst and we'll form our ether, right? So we'll go from ethanol to diethyl ether. And then of course you'll get your H plus back because it's a catalyst. Let's think about the mechanism here. We have our alcohol, we have an acid, we're going to have an acid-base reaction to form our water molecule over here. And then whenever we form this water molecule, now we've got a good leaving group. And then, of course, we've still got some ethanol floating around, which is a relatively good nucleophile. And so it can undergo an SN2 reaction, right? So it's going to do that backside attack to form our product. Of course, this still has the H attached to it. And then you can just have a proton transfer from either another ethanol molecule or water molecule or something like that to go back to our ether, right? So again, the H plus acts as a catalyst. Again, this can only be done for simple symmetrical ethers because if you have multiple components, they might not combine in the way that you want them to. If you want a little bit more control over it, what we have to do then is use the Williamson ether synthesis. Which isn't too complex either. Basically, what you do is you take an alcohol, right? I'm going to call this R1. That'll just be whatever substituent you want on there. You add some kind of base, generally sodium hydride, because then the hydrogen gas just leaves, right? So this will be an acid-base reaction to get this RO minus. So we're going to deprotonate that H. And then you just add an alkyl halide to do an SN2 reaction to install your two new substituents, right? So in terms of this acid-base reaction, right, what we're thinking about is this. We have our hydride, our H minus, picks up this H plus, and then leaves you with this O minus. And then, of course, for this SN2 process, we have our R1O minus, and then we have our R2X. And we just do a backside attack, an SN2 reaction to get to our final product. Note that since we're doing an SN2 reaction, we're going to have some limitations, right? So let's think about the limitations here. Again, what we're thinking about here is an SN2 reaction. So that's that backside attack. And remember, similar to the alcohols chapters, in order to do this backside attack, the alkyl halide has to either be a methyl or a primary alkyl halide. Otherwise, we're going to get an E2 reaction. So for example, if you wanted to form tert-butyl ethyl ether, we can think about this in two different ways, right? We could either cut this bond here or cut this bond here. If we think about cutting this bond here, what we'd have is this OH and then this ether, and then this would be our alkyl halide. However, if you think about what's going to happen here, once we deprotonate this alcohol, instead of having the SN2 reaction, what we're going to have is an E2 reaction, and we're going to form an alkene instead, right? So you can't go through this pathway because your alkyl halide would not undergo an SN2 reaction. Whereas if you made the ethyl part, the alkyl halide, and then made the tert-butyl part, the alkoxide, now we can perfectly do an SN2 reaction, right? So think about what your two substituents want to be. Of course, check the work along for this, but here's just another quick example. Right? If we think about breaking this bond right here and making this the alkyl bromide, remember that these sp2 do not undergo SN2 reactions, right? So there's no SN2 here. So that component is not allowed to be the alkyl halide. What you want is the ethyl part to be the alkyl halide. And then just go ahead and do an SN2 reaction like so. Again, check the work along, make sure you understand what's going on here.